Welcome to this short video on Spaceship Earth Odyssey to a Circular Economy, a century-long perspective. This is Willy speaking. After an introduction you will see the global material flows from 1900 onwards and the conclusions we draw from this analysis. 50 years ago, Kenneth Boulding coined the iconic image of Spaceship Earth. He argued that humanity needs to acknowledge Earth to be a single spaceship, without unlimited reservoirs of anything, either for extraction or for pollution. The circular economy is seen to be a strategy to stay within such planetary boundaries. We investigate changes in circularity and scale of the global biophysical economy over the last 115 years, employing a socio-metabolic systems approach covering all socio-economic material cycles, material stocks and resulting waste and emissions. To this end, we trace all flows of materials through the global economy. We start with the extraction of primary materials from the biosphere and lithosphere, continue with the use for providing energy or materials to the society. Material applications either accumulate in stocks of buildings, infrastructures or machinery, or are used as throughput materials such as fertilizers. Finally, we account for all outflows of waste and emissions to the environment. We consider material loop closing within the global economy and call this socioeconomic cycling. We also account for renewable biomass that is circulated via ecological cycles in nature. We call this ecological cycling. A step-by-step explanation how we trace material flows through the economy is shown at the end of this video. The next images display results of our analysis in so-called Sankey diagrams. These are flow diagrams where the width of the arrows is proportional to the size of the material flow. Based on the analyzed flows through the economy, we can assess the circularity of the global economy. The input cycling rate indicates what share of all processed materials stems from socioeconomic and ecological cycling. The following sequence we show a time lapse of 115 years of social metabolism. In the upper part, the Sankey diagram illustrates the changes in size and composition of material flows through the global economy. In the lower part, you can see how the input cycling rates developed. The ecological cycling rate shown in green and the socioeconomic cycling rate in gray. Both sum up to the total input cycling rate. Watch yourself. After watching all these Sankey diagrams, we find in this graph that circularity declines rapidly after World War II. The input cycling rate that is shown plunges from 44 to 30% within only 2 decades, mainly because renewable biomass loses significance in society's metabolism. In spite of considerable improvements in recycling in the last decades, the contribution of socioeconomic cycling remains low. Since the turn of the new millennium, circularity has not improved. But to remain within planetary boundaries, the absolute size of non-circular flows is even more important than the cycling rates. And these have been growing throughout the last century, from 4 to 70 gigatons per year. This rise is the combined effect of a growing metabolism and declining circularity rates. One important underlying driver for the growth on non-circular flows is the expansion of stocks of buildings, infrastructures and durable goods. The size of these material stocks grew 27-fold. Material stocks require large quantities of material for production, maintenance and operation. Their growth drives the increasing demand for metals, minerals and fossil materials. At the same time, stock growth retains materials from potential recycling for a long period. So, overall, what insights can be drawn from this century-long perspective? Next to improving recycling, realizing the transformative potentials of the circular economy requires addressing 4 key challenges by research and policy: stabilizing the size of material stocks, avoiding non-renewable, unsustainable biomass production, integrating decarbonization strategies with the circular economy, and prioritizing absolute reductions of non-circular flows over maximizing circularity rates. Thank you for watching. If you're interested in a step-by-step explanation how we trace flows through the global economy, watch the remaining slides. If you're further interested, read our article of the same title as this video in Resources, Conservation and Recycling. The following images give you a step-by-step explanation how we trace the global economy's material flows for our analysis. We display flows on Spaceship Earth in so-called Sankey diagrams. These are flow diagrams where the width of the arrows is shown proportionally to the material flow quantity. Based on our results, we can assess the circularity of the global economy. We distinguish non-renewable materials. These are fossil fuels and minerals and metals, and renewable biomass. We start with the extraction of primary materials from the biosphere and lithosphere. Together with recycled secondary materials, they constitute all materials processed in the global economy. We then distinguish 2 main pathways of use. Materials can be used to provide energy, technical energy, but also energy for the metabolism of humans and livestock, that is food and feed. Or they are used in material applications. A small part is used in a dissipative way, such as fertilizers or lubricants, and goes straight through the economic system. The by far largest fraction of materials is used to build up stocks of buildings, infrastructures or other durables. The material stocks box shows how much materials have accumulated in long-living stocks. In some processes, emissions and water vapor are emitted from these materials. Through their use, all materials that enter the economy are ultimately transformed into solid and liquid wastes, emissions and water vapor. In our model, we denote all of these waste products of the social metabolism as interim outputs. A fraction of these interim outputs is recycled or downcycled. These secondary materials feed into production processes as secondary materials. This is what we call socioeconomic cycling. What remains, and this is currently the much larger flow, is returned to the environment with or without further treatment. Some of the outputs, the waste and emissions that result from the use of renewable biomass, re-enter ecological cycles and contribute to new plant growth. We call this ecological cycling. From tracing all these flows through the economy, we can calculate a number of indicators to inform us about the circularity of the global economy. Ecological cycling comprises all flows of renewable biomass. Since not all biomass that we harvest is produced sustainably, we need to correct this flow for the part that cannot be considered renewable. As a first proxy for such a correction, we use net emissions of carbon from land use and land cover change. This is only a starting point, and in future other processes such as the disruption of the nitrogen and the phosphorus cycles or soil degradation should be factored in as well. Socioeconomic cycling comprises flows of secondary material. These are all re- or downcycled end-of-life wastes. Socioeconomic and ecological cycling flows are additive. This means we can sum them up to arrive at the total cycling flows. Circularity can then be measured on the input and the output side of society's metabolism. We define the input cycling rate as the sum of ecological and socioeconomic cycling flows to total processed materials. The output cycling rate is defined as the rate of ecological and socioeconomic cycling flows to interim outputs. Any difference between input and output cycling rate can be explained by the difference between processed materials and interim outputs, that is, by net additions to stocks.